Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel. Today's topic of discussion is additional math operations involving complex numbers. Our objective is to examine operations involving complex numbers necessitating intermediary conversion, isolating individual components of a given complex number, and determining individual components of a given complex number only given partial information. This lecture is predicated on the assumption the viewers watch both the complex numbers rectangular to polar conversion and complex numbers polar to rectangular conversion lectures available at the Big Bad Tech channel. If you haven't watched these lectures yet, or only dimly recall their contents, please take the time to do so now. If you recall in the aforementioned lectures, we learned to convert a complex number using a rectangular format characterized by a pair of numbers, a real horizontal x component plus or minus an imaginary vertical y component times j, to an equivalent polar format, also characterized by a pair of numbers, a magnitude z acting at a specific angle, theta, and vice versa. Rectangular format is especially well suited to perform the acts of addition and subtraction of complex numbers, whereas polar format is especially well suited to perform the acts of multiplication and division of complex numbers. The obvious problem with our relationship are those occasions in which we are presented complex numbers in rectangular format and asked to perform multiplication or division, or, equally as problematic, presented complex numbers in polar format and asked to perform addition and subtraction. While these techniques are possible, they're cumbersome and unwieldy. A far better means of performing these desired functions is to first convert the arguments into a format suiting the desired function and then performing the necessary actions. If the final answer must be expressed in a particular format, one can always reconvert as desired. Let's first consider the act of adding and subtracting complex numbers making use of polar format first. Polar format isn't well suited to the acts of addition and subtraction, so the easiest way of doing this is to first convert the numbers to rectangular format, then add or subtract them as necessary, and if the final answer must be expressed in polar format, reconvert the result in rectangular format back to polar. Allow me to demonstrate. Consider complex number A, represented in polar format as 9.0 at an angle of positive 24.3 degrees, and complex number B expressed in polar format as 9.6 at an angle of positive 153.4 degrees. We're being asked to perform the operation A plus B. When we convert A to rectangular format, we arrive at 8.2 plus j 3.7 as these operations illustrate. When we convert B to rectangular format, we arrive at negative 8.6 plus j 4.3 as these operation chains illustrate. With both complex numbers expressed in rectangular format, we are now free to add A and B together, keeping the real with the real and the imaginary with the imaginary. Doing so, we arrive at an answer negative 0.4 plus j 8. If we needed to express this answer in polar, we could do so with another conversion. Doing so yields 8.0 at an angle of 92.9 degrees. Note these rectangular coordinates place us in the second quadrant, and we should anticipate an angle between positive 90 and 180 degrees, and necessitates active intervention on our part for the inverse tangent function. Does adding and subtracting complex numbers using polar format, including an intermediary rectangular conversion, take effort and organization on your part? Yes it does. Is it hard? No, it's not. It's the same techniques we've already performed, only done so in a specific sequence. In summary, to add or subtract complex numbers expressed in polar format, convert the complex numbers to rectangular format, add or subtract as necessary, then convert the result back to polar. Here's yet another illustrated example of manipulating complex numbers using polar format. Consider complex number A, expressed in polar as 3.1 at an angle of negative 110.8 degrees, and complex number B expressed in polar as 0.3 at an angle of negative 45 degrees. We're being asked to perform the operation A minus B. When we convert A to rectangular format, this results in negative 1.1 minus j 2.9 as these operations illustrate. When we convert B to rectangular format, we arrive at 0.2 minus j 0.2 as these operations illustrate. When we subtract B from A, we arrive at negative 1.3 minus j 2.7. If we need to, we can convert this final result to polar. Doing so yields 3.0 at an angle of 116.1 degrees. Note these given rectangular coordinates place us in the third quarter, and solving for the angle necessitates active intervention on our part. Let's put your understanding of adding and subtracting complex numbers using polar format to the test with these example problems. By all means, pause the lecture and try this on your own. Given these arguments expressed in polar format, Perform the necessary conversions and operations expressing your final answer in polar format. If you're tracking, you should have obtained the following results. For our first example problem, A expressed in rectangular format is 1.3 plus J 2.8. B is negative 2.4 minus J 7.4. When we add A and B together, it yields negative 1.1 minus J 4.6. Converted this result to polar results in 4.7 at an angle of negative 103.5 degrees. When we subtract B from A, it yields 3.7 plus J 10.2. Converting this result to polar yields 10.9 at an angle of 70 degrees. For our second example problem, A expressed in rectangular format is negative 3.7 plus J 2.1. B expressed using rectangular format is 7.8 minus J 6.1. When we add A and B together, it yields 4.1 minus J 4.0. Converting this result to polar yields 5.7 at an angle of negative 44.3 degrees. When we subtract B from A, it yields negative 11.5 plus J 8.2. Converting this result to polar yields 14.2 at an angle of 144.5 degrees. All right, hopefully you did well on that set. Let's now examine the act of multiplying and dividing complex numbers making use of rectangular format. Rectangular format isn't well suited for the acts of multiplication and division, so the easiest way of doing this is to first convert the numbers to polar format, multiply or divide as necessary, and if the final answer must be expressed in rectangular format, reconvert the result in polar format back to rectangular. Allow me to demonstrate. Consider complex number A expressed in rectangular format as minus 3.2 plus J 0.6, and complex number B expressed in rectangular format as negative 3.5 minus J 4.7. We're being asked to perform the operation A times B. When we convert A to polar format, we arrive at 3.3 at an angle of 169.4 degrees. Note these rectangular coordinates place us in the second quadrant and necessitate active intervention on our part to arrive at the angle. When we convert B to polar format, we arrive at 5.9 at an angle of negative 126.7 degrees. Again, note since these rectangular coordinates place us inside the third quadrant, this necessitates active intervention on our part to arrive at a proper angle figure. When we multiply A and B together, essentially multiplying the magnitudes and adding the angles, it yields 19.1 at an angle of 42.7 degrees. If we need to, we can convert this result to rectangular. Doing so yields 14 plus J 12.9. Does multiplying and dividing complex numbers using rectangular format take effort and organization on your part? Yes, it does. Is it hard? No, it's not. It's the same techniques we've already performed, only done so in a specific sequence. In summary, to multiply or divide complex numbers expressed in rectangular format, convert the complex numbers to polar format, multiply or divide them, then reconvert the result back to rectangular format. Here's another illustrated example of multiplying or dividing complex numbers using rectangular format. Consider complex number A expressed in rectangular format 6.9 plus J 5.0, and complex number B expressed in rectangular format as 5.7 minus J 0.3. We're being asked to perform the operation A divided by B. When we convert A to polar format, we arrive at 8.5 at an angle of 35.9 degrees as these operations illustrate. When we convert B to polar format, we arrive at 5.7 at an angle of negative 3 degrees. When we divide A by B, it results in 1.5 at an angle of 38.9 degrees. We now need to convert this result to rectangular. Doing so yields 1.2 plus J 0.9. Let's put your understanding of multiplying and dividing complex numbers using rectangular format to the test with these example problems. By all means, pause the lecture and try this on your own. Given these arguments expressed in rectangular format, perform the necessary conversions and operations, and then express your final answer in rectangular format. If you're tracking, you should have obtained the following results. For our first example problem, A expressed using polar format is 11.3 at an angle of 30.9 degrees. B expressed using polar format is 7.2 at an angle of negative 116.2 degrees. When we multiply A times B, it yields 81.9 at an angle of negative 85.3 degrees. Converting this result to rectangular yields 6.7 minus J 81.6. When we divide a by b, it yields 1.6 at an angle of 147.1 degrees. Converting this result to rectangular, it yields negative 1.3 plus j 0.8. For our second example problem, a expressed using polar format is 7.5 at an angle of 156.5 degrees. B expressed using polar format is 6.6 at an angle of negative 90. Note this is all imaginary in the negative direction. When we multiply a times b, it yields 49.7 at an angle of 66.5 degrees. Converting this result to rectangular yields 19.8 plus j 45.5. When we divide a by b, it yields 1.1 at an angle of negative 113.5 degrees. When we convert this result to rectangular, it yields negative 0.5 minus j 1.0. Let's now examine additional math operations involving complex numbers. We'll start slow and pick up the pace and intensity as we move along. Let's first look at the means one uses to disassociate specific components of a complex number. Given complex numbers in either rectangular or polar format use a pair of numbers, the real and imaginary components in the case of rectangular and the magnitude and direction in the case of polar, one is often asked to determine only one of these components. This is the easiest of tasks if you're even the slightest bit organized and capable of converting between the formats. Consider complex number a expressed in rectangular format as 4.3 plus j 8.9. If we're being asked for the real component only, the answer is quite simply 4.3, because it is the horizontal real x component of the complex number a. Similarly, if we're asked for the imaginary component only, the answer is quite simply 8.9, because it is the vertical imaginary y component of the complex number a. If, however, we're asked for the magnitude only, this necessitates a conversion. One determines the magnitude of the polar equivalent as the square root of the sum of the squares of the real x and imaginary y components. Substituting our given values, we will find a magnitude of roughly 9.9. Finally, if we're asked for the angle only, this also necessitates a conversion. One determines the angle of the polar equivalent as the inverse tangent of the imaginary y over the real x. Substituting our given values, we find an angle of roughly 64.2 degrees. Don't make these disassociation actions hard. All they're asking to do is isolate specific components of complex numbers: real, imaginary, magnitude, or angle. The only time it ever gets even remotely hard is if you have to perform a conversion prior to solving for a specific component not present in the given format. Put your understanding of these tasks to the test with this set of example problems. Given a complex number in a particular format, determine the real, imaginary, magnitude, and angle components. By all means, pause the lecture and try this on your own.